IEEE Census Council KIT Student Branch Chapter, and the School of Electronics Engineering, KIT deemed to be university. It is my pleasure to welcome you all to this distinguished technical talk organized as part of the celebrations of IEEE Day 2025. We are honored to have to host Dr. Debi Prasad Das, Senior Principal Scientist and Head of the Process Engineering and Instrumentation at CSIR IMMT Bhubaneswar. Today, he will speak on soft sensors in industrial process monitoring, a subject of growing importance as industries adopt data-driven sensing, modeling, and control. Dr. Das has contributed extensively in areas such as active noise control, adaptive and EEG signal processing, hardware-suitable algorithms, instrumentation for mineral processing, and industrial image processing. His work seamlessly bridges theory and practice, advancing both research and industrial deployment. He has received several honors, including the Orissa Young Scientist Award, the CSIR Young Scientist Award, and recognition as the Jigyasa Nodal Scientist at CSIR IMMT for his outreach and student engagement. With this blend of rigorous research, applied innovation, and industrial impact, Dr. Das is uniquely positioned to share insights on soft sensors as a bridge between classical instrumentation and data-driven approaches. Please join me in extending warm welcome to our distinguished speaker, Dr. Das. Over to you, Dr. Das. You may start with us.
Okay, thank you, Mr. Srivastava, for your introduction. And may I know the audience, what type of audience, like all students, faculties, or they're all online attending or physically there?
Yes, sir.
The students' attendance are more, or faculties are also there?
Some faculties are also there, but majoritarily we have students with us.
Okay, very good. So I am presenting my slides now. So the talk will be about 45 minutes. Then we can have some discussions. You can share your thoughts, requirements, or some ideas. Am I clearly audible? Slides are moving?
Yes, sir. You are both audible and the slides are visible.
It's also moving?
Yes, sir.
Okay, thank you. So the title as this particular sensor, IEEE Sensor Council deals with different type of sensors and their applications. And soft sensor is a type of sensors. I am thankful to Sudhakar sir who has chosen me for this particular talk. Hopefully this will give some insights of different type of soft sensors that can be used. And in this particular talk, I will be explaining and also discussing about some of our soft sensors which we have designed and also published. So first I will be introducing to soft sensor, then what are the applications in industrial process, then some of our research to particularly mineral processing applications, then we'll conclude. Before I start, I may be permitted to tell a few things about my institute. This institute, CSIR Institute of Minerals Metals Technology, is one among 37 laboratories of CSIR. CSIR stands for Council of Scientific and Industrial Research. It has got 37 laboratories, which was established in 1942. CSIR IMMT is popularly known as Regional Research Laboratory till 2007 from 1964, and it is renamed as Institute of Minerals Materials Technology to focus on mineral and material research. And today CSIR IMMT is the first choice for most of the mineral-based industries, India and abroad. And in CSIR IMMT, we are a department named as electronics instrumentation and control, where our team is working towards electronics instrumentation for mineral processing industries. We also apply machine learning, AI, IoTs for different applications. We also have team for process modeling using computational fluid dynamics and discrete element methods. And a team also working towards molecular modeling, where chemistry is modeled using molecular dynamics and density theory. And all these are related to soft sensors. You know, automation. This particular picture is maybe well known to you. This is a washing machine, and you can see sometimes washing machine was just a manual washing machine. So there is a motor; it will rotate, and it will churn the water along with cloth and soap, and then what? And the particular cloth gets cleaned, and you have to by hand you have to remove and squeeze, rinse. Everything is done manually. Then came the semi-automatic. So by putting some sensors and like water level sensors or a timer to run, all these were made to make it little automatic called semi-automatic. Then next came the automatic washing machine. But still the automatic washing machine, which is you just put the cloth and put your timer or the particular parameter or particular set point, then it will particularly run and then do the things. But still there is scope of improvement. You can add more functionalities by cloth based. It can actually see the cloth and do itself setting. So automation, fault monitoring, optimal performance, all these require different type of sensors, and standard sensors are not adequate or available for indirect sensing for many things like the type of cloth. There is no sensor which can see the type of cloth or the amount of cloth you have put. So we cannot put a load cell there. You can do different way of sensing the same thing. So those are called soft sensing. And the AI ML algorithms are used in a big way in designing soft sensors. So I will be defining soft sensors and also tell something more about it. So this is a table which clearly distinguishes a conventional sensors. As all of you know that sensors are to measure a particular process variable, like temperature sensor or a pressure sensor or flow sensors. Those are available. But what about the size of a particular material while it is being produced? So it is not available. How to measure the concentration while it is running? How to measure how to monitor the cooking process to know whether the cooking is complete or not? So there, what we do is we put some indirect measurement and then put algorithms and models that estimate unmeasured variables using mathematical models and some indirect measures. Suppose from temperature, you can measure the pressure. From temperature, you can also measure the health of the battery. From temperature, you can also measure the health of a particular person. So those all are indirect measurement. So direct measurement type is called direct measurement, conventional ones, and the soft sensors, they are also called virtual sensors or software-based sensors. So to make a soft sensor, you need a computational algorithm. So a computer is required, a mobile phone is required, an FPGA may be required, a microcontroller may be required. So those all are required so that algorithm can run on them. So these are the examples like estimation of concentration, viscosity, reaction rate, biomass, calorific value, all these direct measurements are not there. So indirectly from the temperature, from the mass, you can measure, find out the calorific value. The cost of we cannot say that soft sensor can be lower or higher, but they are having a lot of advantages. And advantage is the most important advantage is the places where there is no sensor exists to like availability of variables. limited to variables for which sensor exists. So there is no sensor suppose available. What is happening inside a blast furnace? There is no sensor to see there. You cannot put a camera inside the blast furnace. Temperature is very high. So what is happening? Can you map it? Suppose in one room a person is there, from the other room can you sense it without putting a camera? So it can provide impossible to measure variables like inner cell states, internal states of chemical reactors. For scalability, so uh, sometimes it is told that it can be soft sensors are easy because you just change the software, it will work for a higher range variable. Suppose you have a temperature sensor for certain range, 0 to 1000 degree. But to that, for changing to 0 to 2000 degree, you have to change the sensor. But for software, soft sensor, you may little bit modify the algorithm and it will work for a different range. So it's called scalability. Okay, and the applications are widely used in all industries. Conventional sensors. Today's instrumentation people and the operation people, they rely mostly on the direct sensors. But in future, we will be increasingly using the soft sensors in future because of the advent of Industry 4.0, Industry 5.0. They are called digitalization. There are the companies, the processes are becoming digitalized. So indirect measurement and that is called soft sensor. Some examples let me tell so that you can appreciate. So for example, concentration of a solute, ion or chemical. So I cannot just go and count the number of solutes in terms of moles per liter or something like that. But suppose I know the conductivity, the pH, the spectroscopic signal, then soft sensor I can model them. I have some standards. Then I calibrate. Then I can have a sensor which can measure the concentration of solute. For example, pollutant concentrations in wastewater. So those can be used. The main sensors will be conductivity, pH, and other spectroscopic signal. But they all will be input to my software, and software will then do some calculations and then finally find out the concentration of heavy metals, concentration of some other things, a particular chemical or antibiotic or something like that. So biomass concentration estimation using oxygen uptake, CO2 evolution rate. Suppose there is a biomass reactor. Biomass means some woods are there or something you are burning or something like that. Then how much oxygen it is taking and how much carbon dioxide is generating. Okay, so that from there you will be able to know, for example, fermentation or biotech reactor, viscosity, moisture content. Suppose there is a material, there is a moisture inside. Moisture means percentage of water in the material. For example, 1 kg of material, you have suppose 100 gram of water inside it. So it is called 10% moisture. Okay. So how to measure 10% moisture? So I will put a microwave on it and I will detect the reflected microwave or the transmitted microwave and see how much microwave it is absorbing. Because I know that water absorbs microwave. So if I put microwave with some particular amount of microwave power is absorbed, then I can say this is the amount of moisture. So this can be used in kilns, dryers, and food industries. Suppose gas composition, I might know, but I do not have a particular carbon monoxide or hydrogen or this sensor. I don't have, but I can estimate it using calorimetry. What is calorimetry? How much is the heat it is generating or it is absorbing? The calorie of it. So heat energy. Basically, it is a container having some water, and it is getting heated. So cold water is having inlet and there is an outlet water. By just knowing the mass of the water and the inlet temperature and outlet temperature, I can know the calorific value. Means the calorie value of how much heat it is absorbing. So that is called calorimetry. Then infrared absorption. So how much infrared it is absorbing. Then by solving material and energy balance with flow and temperature data, I can estimate carbon monoxide, because if more carbon monoxide, it maybe infrared, some particular wavelengths will be absorbed, and some other things will get changed. Okay, but they are not linearly related. Had it been linearly related, CO2 and infrared absorption, I would have said it is a CO2 sensor, but they are not linearly related. It's not one variable related to this. Okay, that is why you require soft cell. Slurry density. Suppose there is a pipeline, we put nowadays, ores are mined from mine site, and they are not supposed to be transported by trucks and trains, because that will create environmental pollution or damage to the road and all. So you can put a big pipeline and just make a slurry, like you grind the minerals and put inside the pipeline, and the pipeline will carry it from long distance and it can reach. And if it is a slope, then it will automatically pump. Otherwise, in between, you have to put some booster pumps. But suppose the inside there is a high concentration of slurry and it is settling and it is getting choked, then the whole pipeline you have to remove and you have to monitor where there is a choke. It is not visible to outside. So for that, in between you have to put the pressure sensors, ultrasonic velocity meter, gamma ray attenuation, all the sensors data you get, and from there you will be able to know and locate what is the slurry density at what particular position. Reaction rate conversion, calorific value of the fuel, level of an opaque vessel. There are silos where the materials are kept inside. First, the raw materials are kept. There are big silos, and you need to know, suppose, what is the level of the material inside. It's not visible to outside. You are feeding and you are also discharging from the bottom. Then, can we know from the vibration, from the acoustic emission? For example, I will tell you a big drum, suppose, containing water. Now, I cannot see inside how much is the water content. Can you just strike the drum and listen the sound? If it is full, then sound will be different. If it is half, sound will be different. If it is empty, sound will be different. So from the sound, if you can know the level of the particular opaque vessel, then they are called soft sensor. Suppose a ball mill is there are liner inside, suppose they are worn out. Their wear and tear happens. They are broken or they are damaged. So from outside, how will you know? If you are experienced, that you know that when the grinding mill is having good liner, then power consumption is less. When the liner are damaged, they start consuming more power. So power is the indication of that. You know that vibration is some erratic vibration is coming when the liners are different. So vibration can also give the information. Acoustic emission also. Suppose there is some change in the grinding mill inside the mill, then that also gives some information. So those are called soft sensor based systems. So for doing the soft sensor, as I told you, have to take any sensors, physical sensors, which are not directly related, but they are interrelated, and those sensor signals are captured by a computer. Once it is captured, then you have to do some signal processing. So that signal, which is coming from conventional sensors, they are called signals, and signals are required to be processed by using some algorithms. They are called signal processing algorithms. So what are the purpose? If there is a noise, you have to remove. So that is done by filtering. You can extract features. Suppose a signal is coming, you can know how much is the high frequency component, how much is the low frequency component, what is the mean of the signal, what is the standard deviation of signal. Okay, so there are statistical information, there are some signal processing information. You can use Fourier transform or Wavelet transform or PCA to extract information. Then so many sensors are there, then you have to add them, they're called data fusion. Then if the data has got a drift or fault, then that also has to be identified, because you have the soft sensor that is very intelligent to know that the data which is now coming is fault. Maybe the sensor which is attached, there is a it is loosened, the knot bolts are loosened, that is why the signal is not coming. So that is called fault. It has to detect. It should not process a faulty signal and give a wrong information. Okay? Dynamic modeling and state estimation with respect to time, it will model, and it will handle the time varying process. Suppose now something is happening, after some time the process will be different, so therefore time varying process. So there are some autoregressive moving average models, so they can estimate the internal reactor. Suppose there is a reactors are for reactions. Okay, so you can do some chemical reaction inside a reactor, and reaction will start and end. But when it is starting, when it is progressing, and when it is ending, so you need to know the from outside the state of the reactor, the state of the reaction. Okay, so that is called state estimation. Okay, so am I audible?
Yes, sir, you're audible.
So is it okay for you? Till now you understood what is soft sensor? Can anybody tell what is soft sensor? Because you all are students, I can ask you questions. Anyone online tell what is a conventional sensor and a soft sensor? The indirect way of measuring something which is impossible to measure, right? Using conventional sensors and signal processing and AI/ML algorithm. So this is called signal processing algorithm. Then I talk about some uh, some AI/ML algorithms. Okay, so as you know that we have got how many sensors? 5 sensors. Okay, so we can see, we can smell, we can taste, hear, and touch. But only with 5 sensors, how many varieties of monitoring we can do? The teachers can monitor the students, right? The teachers can check the answer sheets. Okay, if some teachers are teaching, you can understand the concept. Okay, because of only these sensors and your brain. So with limited number of sensors, multiple varieties of work you can do. Like you have a smell sensor, it's many types of things you can do. You can use the smell sensor for your cooking. You can use the smell sensor for some other applications. Okay, using the touch, you can drive. You can sense the temperature. Okay, so like this, industrially also we can design soft sensor where the known sensors can be taken and the brain will be trained for that. Suppose a small child cannot sense a hot and cold, so he will just touch and then you will know that, oh, this should not be touched. A candle is suppose glowing, then a kid, very small child, can go and touch because he has never experienced. Okay, but we have previously experienced, so we can never do that. Okay, that is called soft sensing and knowledge discovery. Since human has got only limited number of sensors, still it has got very intelligent visual perception, speech recognition, decision making, and translation between languages. Those all are done using machine learning, as you may be knowing supervised learning, unsupervised learning, and reinforcement learning. So if you say that suppose inputs are, some sensors are having inputs, and you have to generate some output, so in between there is a mathematical equation. You have five sensors, suppose temperature, pressure, flow, and smell, let's say, gas sensors. Okay. Now output is whether the reaction is complete or not complete. Then you have to do some mathematical calculation in between. So they can be an equation like this, or they can be very complicated like a deep neural network. Okay, so input and outputs are related by a very uh, complex model, or it can also be a very small linear model. Okay, so they are called modeling. So modeling is very much required in soft sensor. Like in the first, here we have said these algorithms or models. So what is soft sensor? It's nothing but an algorithm and model that estimates unmeasured variable using mathematical models and measured inputs. Is that clear? Hello.
Yes, sir.
Okay. So let us make it interactive. So as you know that model can be a linear model or a nonlinear model, can be a neural network. This is called a back propagation neural network. So to model the neural network, you have got cost function, classification cost function. There are varieties of things. So this is a different area. But this AI ML algorithm has been used and is a very important aspects in soft sensing. So next we will be telling about the different type of soft sensors and their requirements in mineral processing. Okay. So what is mineral processing? Mineral processing. Okay, I will go to another slide. This one. Mineral processing means, since our institute is mineral processing, though we know varieties of soft sensing applications, but we apply only for mineral processing applications. So ores are there, iron ore, let's say. You have seen steel, but how the steel has come from a rock or from a ore. Okay? So there are a lot of steps used to get the steel or iron. So first is you take a lumpy iron ore like this, the left one side, and they are basically low grade ores. If it is a high grade ore, high grade means it has got 65% of iron content, the whole thing. So you can directly put in blast furnace and melt it. You can do the reduction. Iron oxide Fe2O3. But to make it Fe, to remove the oxygen, so blast furnace are used, DRI is used, direct reduced iron process is used. But if it is 45% or 35% or 30%, then they are called low grade ore. And these low grade ores will be crossed to make fines like this. Why crossed? Because suppose if you break the particle like this, the red ones are important ones and the gray ones are actually not required. So you have to break into these small pieces. Then you separate the red ones from the gray ones, so that the concentration is improved. So the gray ones you have to throw and only keep the red ones. So if you throw some of the gray color ones, then you will find the concentration percentage is improved. So from 45% may go up to 65%. So while doing this, what you are basically doing is you are breaking the particles to smaller size, and these smaller size particles cannot be charged to blast furnace. Blast furnace require a particular size of ore, but to convert this big size ore or extract the minerals from the big size ore to improve its concentration, the grade, we are breaking it to fines, smaller size. So we have to again, first we grind, then we have to separate. Therefore, screening, classification, gravity separation, all these are used for separating them. Then these fines are called high grade fines. They will go to agglomeration. So while doing this, you have to add water and do some processing. So that is called slurry. And this slurry has to be dewatered. Dewater means remove the water from this, so that by the process of drying, you have to make again uh, powder materials like this. And these powder materials will be made into very spherical balls. The spherical ball size will be 8 mm to 16 mm required size, and they are the pellets. Now these pellets can be used in blast furnace. But the whole process requires a lot of processing. Okay? You can separate using magnetic separator, electrostatic separator, fluorescence, electric flocculation, all these are processes. So a typical flow diagram is like this. So it is a raw material handling system, raw material. Then you have to cross it, primary process, then screen, separate it, bigger and slightly smaller particle. Bigger will go to the secondary processor, light smaller will come here. Put water, then again grind or scrubbing. Scrubbing means separate the clay material or something like that, separate it. Then whatever is the output, you put into a spiral classifier or hydrocyclone. They will separate the lighter fines, rejects into the concentrates. Okay. Then you have to use magnetic separator to separate something. You have spirals, you have many operations are there. Then it will create something called, if you have a lumpy parts, you have a lumpy iron ore part, you have very fine ores, and you have pellet fines, which are suitable for pellet making, spherical ball making. So this is a process which is regularly used in industry. Depending on the ore, these process steps may change. And this one is called the pelletization. From the fines, there is a circular disc to rotate, and the fines will be converted to spherical balls. They are called green pellets. Then they will get into a furnace of high temperature, about 1300-degree temperature, to harden it. So hardened spherical balls are called indurated pellets, and they are actually called product pellets. So from the raw material to product pellets, there are different processes. They are called mineral processes. Okay, and the product pellets can go directly to blast furnace, and you can get iron from there. So for grinding, you have grinding mills. Okay, but what are the issues while grinding? Suppose you have a grinder at home, you are grinding. So when you are grinding, uh, your mother or whoever is using, they will be able to, from the sound, they will be able to know whether the grinding is complete or not complete. Okay? Similarly, inside the ball mill, whether the grinding is complete or not, can we know from the vibration? Whether the blade of the grinder is broken in the home grinder. In the ball mill, whether the balls inside the grinders are worn out, can we know from the vibration? Can we know from the power drawn by the mill? So they are called the soft sensors. So this is inside of a ball mill. So there are a lot of balls inside. These balls actually rotate along with the material, so that the red ones and blue ones are separated. Okay, they all are mixed, but they are dislodged from this, and then you have to do some kind of differentiation by classification and screening. Basically, classification using gravity or magnetic separator. Then, if these red ones are magnetic, these are non-magnetic, then magnetic separator will be used. If they are all are non-magnetic, then that is not going to work. So you have to use some other process to remove. You can use flotation by putting some kind of chemical. You have to float it and generate. So all these are different types of processes. Now, like doctors put a stethoscope on our body and know different parameters. about our information. So can we put a stethoscope on a grinding mill, like a vibration of the mill we detect and know a lot of information inside the mill. So what we did in our experiment in one of the cases, monitoring the fill level of the ball mill using vibration. Means when the ball is there, material is there, what is the level of material, whether it is half full or less than half, or 10% or 20% or 30% or 40% or 50% full or more than that. Can you know while it is running from the vibration signal? So it requires a soft sensor. We cannot do by any other method. Okay? So for that, what we did is we put a vibration sensor, and the vibration sensor is nothing but an accelerometer, and the accelerometer signal looks like this. So it is a triaxial accelerometer. From this signal, so many signal looks like noisy. So many signals handling is difficult. So you have to extract the features using Fourier transform or DWT or WPT or EMD, and we extract 10 features or 11 features or some high number of features. Okay, they are numbers. So if this input is given, 10 numbers will be out from here, and a neural network is used to train. And once we train it, then from the vibration signal after the feature extraction, then it is able to uh, estimate the field level. So this is not called measure the field level, this is called estimate the field level. So the dark light, which is called the actual field level, but from the vibration we are able to estimate their nearby 10. It is 10%, 20%, 30%, 40%, 50%. So they are all. So this is small work we did, and this can be found in neural computing and applications. Some more experimental results will be available there. So this is one application of soft sensor, where the actual sensor is a vibration, but output measurable quantity is the fill level of the ball mill. Then another particular, as I told you, that the fine slurry, inside the fine slurry, there will be some highly concentrated things, means high density items, and there are some low density items. Like, cyclones are there. When cyclone comes, super cyclone, which items are flown away? The lighter items are flown away. Heavier items are kept at the bottom. So they are called a cyclone in the atmosphere. Now it's called hydrocyclone. When the water is going in a tangential direction in a conical apparatus like this, they rotate cyclonically so that heavier will go down, lighter will go up, and they are separated by this. Okay, so by this heavy and light can be separated. But what happens sometimes, because this is a narrow outlet, sometimes they get choked. When they get choked, if the concentration of slurry is high, if some other the velocity may be high, okay, the pressure is different, then there may be choking. So in that case, because raw material is coming, raw material has got variability in concentration, the material content, so there is a possibility of choking. So can we estimate the choking, whether choking is going to come after 5 minutes or not? If I estimate, then I can actually stop flowing of the slurry, high concentrated. I can add some water and make it dilute so that it will not choke, right? So when we operate, we find the output discharge pattern. Discharge can be like this. It's called spray discharge. Discharge can be like this. It is called rope and spray. So it will combine discharge. And discharge can be rope type. You can see here, only water is given. The discharge is like this. Some slurry, low concentration, high concentration. Slowly, slowly, we are increasing the concentration. We find after some time it is getting choked. It's not coming out. Whatever is getting fed, they are not coming out. That means material has built up here. And once it is choked, it means it is a trouble to the industry. They will stop and open and clean. Difficult. Okay. So slowly, slowly we increase the concentration, then we decrease the concentration. We find again it is coming to the spray discharge time. So this experiment we did for different known concentrations, and we captured the vibration. Okay. Then we plotted the fast Fourier transform, FFT. Okay, and we found that when there is nothing is there, dry run, so water is run, but water is not fed. So there is a peak coming in the Fourier spectra around 21.2 to 21.3. Then as soon as we put water without putting any material, then we found this particular peak is shifted left. Then added some little amount of material, about 4%, we found suddenly it got shifted. So how we got this information? Because we have captured the vibration signal for all these varieties of concentrations. And then at home, we analyzed by taking the Fourier transform, zooming the area. Around this area we zoomed and we found that this particular peak is shifting. Then we correlated and found that if the concentration is increasing, this is decreasing, and around this concentration, choking happens. So if we are supposed to run at this particular concentration, maybe blue color one, or maybe this particular color one, this purple or somewhere. Now suppose there is a shift towards left side, then immediately we should alarm that choking is going to come, don't increase the concentration. Put some water and dilute it. Okay? So then this is by increasing concentration, then with the same thing we decrease the concentration and found that same peaks were shifted right side. Okay? So this one was 31% was there. How we increase and decrease concentration is by adding water. So while to increase the concentration we add solid. To decrease the concentration we add water. Okay, with the same tank only. So this shows that by doing signal processing we are able to check the frequency and do the checking of the slurry concentration as well as we understand about the choking practice. This is soft sensor. So another frequency range 40 Hz also it is coming, 60 Hz is coming because it is shown in the harmonics. So 40, so 20 was there, first harmonic and second harmonic they are in 40 and 60 range. Okay. So next another process is called plasma processing, where we are feeding argon and hydrogen inside a particular plasma reactor. So plasma is nothing but two electrode. When you spark and give a gas of argon and hydrogen, this particular area will be ionized. Plasma is nothing but an ionized gas, as you know, solid, liquid, and gas. And if you give energy to the gas, some of the elements or molecules they get dissociate. Sometimes some elements will be ionized, means the electron is removed. Some will be excited, some will be in the neutral state. So electrons will be there, ions will be there, neutrals will be there. That particular area is called plasma. So in the plasma, in one of our experiment, we were using hydrogen and argon, and hydrogen is very risky, as you know. So in case there is a leakage in the hydrogen pipeline, then we cannot know because flow meter will show that hydrogen I have sent, but in between there is a leakage, the proper hydrogen is not coming. So what we did, we thought from the glow, from the light, the intensity of the light and the spectra of the light, can we know what is the hydrogen? Because when the hydrogen is there, a lot of spectral lines will come. Okay, some spectral lines. Spectral lines means, as you know, light has got different wavelengths, and each wavelength, some peaks will be there. They are called spectral lines, and each wavelength corresponds to some elements. Okay, and we have a spectrograph, which is a very expensive one. It's called high resolution spectrograph. So from the light of the plasma, we get the spectra, and from the features from the spectra, we trained a neural network to estimate the hydrogen flow rate. So the paper is published in neural computing application. You can see that actual is 5 liters per minute, And from the spectra also we are estimating 5. Here also 8, then 10 and 12. In all cases, we are almost estimating it to be very, very correct. Okay, so this is a redundant sensor because already flow meter is there for hydrogen. Why you require? Because this can be used as a redundant sensor in case flow meter does not work. This can also give you the information because this will give you the right final information. Okay, that your the plasma is there, but hydrogen has not entered into the plasma. So this is another plasma where there is a crucible type of electrode at the bottom, and there is a cylindrical electrode which goes inside and plasma is treated. From the outside, can you know how much it has gone inside? It's not visible. Okay, how much is inside it has hit. So our objective is what is the cathode position inside the whole thing. So there is no sensor for that. You cannot put a camera because it's very high temperature. Okay. Then what we did is, while plasma is formed, we collected the voltage current signal. They are like this. So when we run at 100 ampere, these are the voltage signals at different distance. The red one is the distance. So 10 mm, 20 mm, 30 mm, 40 mm like this, up to 100 mm. 100 mm means 10 centimeter distance. And the voltages are coming like this. Sometimes it is going somewhere like this, sometimes going like this, at different current is different. So now we are taking this as input and the current also as input and taking some features. We are estimating this. You can see the actual distance is this, but we are, let's say 10 mm, around plus minus 10. 10 it is coming about sometimes 18 or less than 10, like 8 or 9, like this it is showing the result. So maximum error somewhere here we are getting, otherwise most of the cases we are getting the uh, uh, agreeable performance, satisfactory performance. So this is also published in IEEE transaction plasma science. So I am referring those papers so you can get more information. Then we also use image processing. So these are sensor interfacing. Now, can we have camera-based sensors? Camera-based sensing. So, like doctors watch a X-ray image or a CT scan image and do some information extract. Teachers check your answer sheets and find information. Engineers also see by their eye. Drivers watches and drives. So, can we do the same thing the process monitoring using image processing? They are called vision-based instrumentation, or they are called vision-based soft sensing. So, like I know handwritten character recognition. So this is called free, but it's not a perfect free. But even if it is a tilted free or a distorted free, then a CNN algorithm, which is called convolutional neural network, can actually estimate. So image processing can be done using CNN. So we applied this for an industrial monitoring problem called pellet size monitoring. As I told you, the pellets are formed. These pellets are made inside a very big disk, and the pellets, tons and tons of pellets are formed very quickly. Okay, and but the pellet size are not remaining constant throughout the process. That means sometimes it will come at 6 mm, sometimes 10 mm, mean size. So randomly they come and mix of sizes they will come. But what is the size analysis is not possible to monitor. So what we did is we captured the image, did some kind of histogram equalization, image resizing, and applied the CNN networks. And then we are able to know from the size, like the operator is watching and finding out. So we can also operate, we can also do the CNN algorithm and say, no, this size is very small or good or big or very big. Okay, so this is another application. So we capture the image from inside of the disk, and these are the sizes. You can also see from your naked eye. This can be called as a big size, small size, and the lower one, number 5, can be called as a big size. So though they are gradually increasing, but still image processing algorithm can actually tell. So they are also called soft sensor based size monitoring. So then when you use classification algorithm, you have to have confusion matrix and all that. Those are AI ML algorithms performance metrics. But finally, you can see if it is a very small, all the data are showing is very small, but very small amount of data they're saying as small. So little error is there. So for this small cases, some are also showing as good and some are also showing as big. They are the errors. Okay, so little error. So we have actually compared with many algorithms like BGG16 or MobileNet or ResNet or ensemble model and a proposed model. The proposed model, you can see there is no problem at all. Okay, so that is why it got published in two journals with different results. The IEEE Industrial Application Magazine and Naval Computing and Applications. You can refer. So then another is objective is not to just to know that size big or small or this thing, medium size, but to know that in the whole image how many pellets are within this range, 12 to 14, how many are 8 to 12 mm, how many are greater than 16 mm, how many are less than 8 mm. Okay, so that they can know that even if pellets are coming, no, not that all should be 8 mm or all should be 16 mm. There should be a distribution of pellet size. So those for that we capture the image from the discharge and level them, create segmentation, use some kind of CNN network, and then we sort the pellet size distribution, and it worked very well. Compared with some existing algorithms, we used modified UNet architecture. You know, CNN has got varieties of CNN. It's called UNet architecture, which are used basically for segmentation. Segmentation means separating the background from the object. So here object is the pellets, background is the white background. Okay. So like this, the image will come, and then we have to count, we have to detect and count and find out the size. Then we shown that the measured and our estimated are very close agreement in our algorithm compared to others algorithm. So that is why it is also published in IEEE transaction on automation science and engineering. So this is also a soft sensor based size analysis method. Similarly, more work was done. This is a plasma. We put hydrogen gas and we put argon gas and we operate at different current. So by just watching the image of the plasma, can you tell what current it is running and what is the gas flow rate? That was our objective. Can we estimate the current and gas flow rate condition from the image? So yes, so for that we run it with known current and set of currents and gas and no gas conditions. No gas means no argon gas is put. If the gas is applied means 4 LPM of liters per minute of gas is allowed. So many images we captured by making it automated capture image capture scheme. And these are typical images. So we have what 1700 images, but we have shown some 10 images here to just to show that when the current is there, current is increasing, suppose 50, 75, 100, how the image is changing. So slightly glow is increasing. When there is a 50 ampere and 50 ampere with gas and without gas, you can see the difference. So when you apply the gas, it is more consistent. When you don't apply the gas, there is more reddish color. So these are the pictures, but we have not extracted the picture. We just applied the CNN with some standard CNN. We compared, and then all the classes. We did the classification. A lot of algorithm compared, and we found that our algorithm has got best classification, which is also published in IEEE transaction plasma science. So these all are about our contribution to soft sensing and mineral processing. The soft sensor based instrumentation in mineral processing can be improved by use of AI/ML algorithms. So you have to extract, you have to run the process by known steps like different conditions, and then capture the data, then develop algorithms by applying signal processing based feature extraction or deep learning based machine learning. Then attempt were made. In this case, we have attempted to make use conventional sensors like accelerometer, camera, motor diode, temperature sensor, etc. to collect data and use the AI/ML algorithm for ball mill fill estimation, hydrogen fluoride, pellet size classification, pellet size analysis, plasma process parameter estimation. So there is unlimited scope for you to apply. Suppose you put a camera in your vehicle and it will detect the potholes in the road, starting from your village to your place. Suppose you put a vibration sensor on the vehicle, you see that how smooth is your vibration of the vehicle. So soft sensor can detect the road condition from just a vibration sensor or a camera. So opportunity in digitalization, because every industries are now discussing at a higher level on digitalization. Can we add more digitalization? Why digitalization? Because the human manpower is not reliable. Today they are there, tomorrow they will resign and go to another company. So digital computer has to take over the human, and there are certain conditions, there are certain atmospheric conditions where dusts are there, temperature is high, so human operations are limited. So digitalization is very, very important. And Industry 4.0, 5.0, you all know the definitions and how it is going to help in big way in industrial automation and mineral processing and other processing. I told only mineral processing. You can apply for food processing. You can apply for textile industries. You can apply for rock industries, chemical industries, petroleum industries. All these are possible. So I think it took a little more time, but it is all finished. Thank you. So I have completed. If there is any questions,
All right, Dr. Das is open to questions now. If any of you have any questions, you may ask them now.
hope audio is okay.
Yes, sir, it is. Sir, I have a question. Using ML and AI algorithms, these are like very power hungry operations. So when we are deploying sensors in remote locations where we have a limited capacity of power, how are we going to manage that? Like, do you have any specific standard set of procedures that we go through in order to achieve that?
Yeah, very good question. There are applications like electric vehicle, let's say. So we cannot afford to add a power hungry AI/ML application because they also will draw the power from the same battery. So, but if it is industrial installations, there are a lot of powers available there. And if you use this AI/ML algorithm, even by taking some wattage or kilowatts, but saving some other wattage by optimizing the process. For example, you use less fuel in a particular baking process or a roasting process by proper monitoring. For example, the pelletization one I said. So you are using image processing to know the size analysis real time. Why? Because if I don't do the size analysis, they will be very big or very small. They are rejects. So even if it is running, but its product is not coming, so the rejects are waste. So if you consider the product, the energy is lost there. So if you properly monitor, even if you give little bit of energy to your AI/ML algorithm, and still you are benefiting the process. So if you say that no, I want even optimized energy consumption AI/ML. So there are you can constrain them by computational complexity, less number of layers and all that. Then you have to work on optimizing the algorithm so that it will be consuming less power.
Right. Thank you so much for answering my question. This was an enlightening talk. I'd like to request IEEE Census Council's Bhubaneswar Chapter Chair, Dr. Sudhakar Sahu, to now present you with an appreciation certificate and formally deliver a vote of thanks.
Hello. Sir, hello, hello.
We can hear you, sir.
Yes, sir, your voice is audible.
Okay, okay. So now, on behalf of IEEE Sensor Council Bhubaneswar section, as well as IEEE Key Student Branch Sensor Council, Local Electronics Engineering, we are all thankful to our esteemed speaker, Dr. Debi Prasad Das, sir, for giving insightful information about the sub-sensor using machine learning application in industrial process control. Also get many information input so that we can utilize in our student project. Student can also do the project. Okay. So finally, once again, thanks sir for accepting our invitation in short notice. And also, always you are also the value researcher of KIT University as well as us. Whenever you invite, without any hesitation, you are delivering. Once again, with this, thanks sir for kind deliberation to our IIT Council. Thanks, sir. Namaskar. Thank you. And also, I thank to Abhrajit Das, who are the chair of our IEEE Student Bank Censor Council, for very arranging and nice technical talk in online mode. Okay. And also, thanks to Rasmita Madam and all our student member of IEEE Censor Council for arranging such type of activity in related to our business circles. With this, thanks to everybody once again. Okay, sir, namaskar, sir. Thank you, sir.
Okay, thank you for giving opportunity.
Sir, sir, sir.
Thank you, thank you.
Okay, sir.
We also have with us Treasurer for IEEE Census Council Bhubaneswar chapter, Rashmita ma'am. She'd like to give her regards to you as well.
Very good evening, sir.
Good evening, madam.
So whatever I'm listening, the topic was very nice because this is the growing industry. And one of the major slide I was saying that acquisition of the data. Now most of the things are done on the sensor work. So I would request sir to guide our students in this chapters that what is the role of sensor, how the data acquisitions and all the analysis are done by the help of AL and ML. And really the session was very interactive and also very informative. Thank you so much, sir. In future, we'll try to have an offline mode such that students can get more knowledge and the practical applications and the research things going on